Thus far, we have looked at the reciprocal and quotient identities and the Pythagorean identities. In today's lesson for trig identities, we're going to look at the sum, difference, and double angle identities. With some of the other ones, we had a bit of proof involved, but they are very trivial proofs as far as proofs go. And what it would take to prove one like that is a little bit more involved. So, unfortunately, we won't be showing those ones on screen today. They are worth looking up, though, if you want to give them a look-see. But your three sum identities are these ones. So if you have the sign of a sum of angles, called alpha and beta, or A and B, if you will, then you can expand that this way. So we can't just say that we have sine alpha plus sine beta. We can't just say that we're distributing the sign, because that's not how functions work. So when we're dealing with this, the sign of a sum of angles expands to this and this only. We have sine alpha cos beta plus sine beta cos alpha. So never, never, never just say you can distribute the sign. That is, again, not how functions work. Cosine of alpha plus beta is kind of similar-ish, but now we've got the coses together and the sines together. So cos first and sine second. This one involves a minus. And then the tan of alpha plus beta is this behemoth right here. A little bit of a doozy, but there it is. Now these aren't required to memorize. They are on the formula sheet. So they are given to you exactly as they are. We can use these to develop the difference identities. So once we have these identities already existing, getting the difference identities and the double angle identities isn't actually so bad. We'll be replacing all these betas with negative betas, so that we can have the sine of alpha minus beta and the cosine of alpha minus beta. And when we replace these with negative betas, we're going to be replacing these with negative betas as well. Negative betas all over the place. But to see how that links back to the original function, we'll just note some things real quick. Erase, 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 erase. And scroll, 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 scroll. So this is the cosine function. And what we notice is that it's the same on the right as it is on the left. So if you were to take the cosine function and then give it a flip over the y-axis, which would be to turn into that, we'd get the exact same function back. So when we reflect this over the y-axis, it's the exact same function. We can say that cos of negative x is the same as cos x, as in this statement right here. Whoop. Nailed it. When we take something like the graph of y equals sine x and we flip it one way, and say we flip it over the y-axis, we'll get something like this. So that's when we flipped it lefty-righty. If we want it to actually match, we have to take this new graph and actually flip it upsy-downsies. So we have to do two flips to it. So we can't say that sine of x is the same as the sine of negative x. We have to do another flip and say that we're putting another negative in front of that. So that's why we can say sine x is the negative sine of negative x. That's actually called an odd function. So cosine is referred to as an even function, where f of x is equal to f of negative x. An odd function is where f of x is equal to the negative f of negative x. Just a for funsy term there that you can memorize. Be a fun bonus, I don't know. But that's how we can use this business here. And then finally we've got the tan function right beneath here. And this one is also an odd function. So we'd have to flip it twice. We'd have to flip it both we'd have to flip it both horizontally first and vertically. So those flip down, so that we get the original function back. So just like with the sine function, we can say that tan of x is equal to negative tan of negative x. So those are the rules we're going to be using. We can say that cosine of x is equal to cos x. Sine of negative x, if we just manipulate this formula a bit, is equal to negative sine of x. And similarly, tan of negative x equals negative tan of x. So that's what we'll be using to get our difference identities. Over here! So we can take this difference of angles here and express it instead as a sum of, angles. Instead of alpha minus beta, we'll say it's alpha plus negative beta. When it's phrased as addition, we can actually use the sum identity right here as it is. So it looks like that. And then we'll phrase it as something, since the sine of alpha plus beta is, what was it up here? Sine alpha cos beta. Sine alpha cos beta plus sine beta cos alpha, or something like that. So using that info, we can phrase this as sine alpha cos negative beta plus the sine of negative beta cos alpha. Just replacing all these betas with how we replace that first one. From here, we're going to use some facts. We're going to use the fact that cosine is an even function. Cosine of negative x is the same thing as cos x. So we can call this just cos of beta. And over here, we're going to use the fact that sine is an odd function, and that sine of negative x is the negative of sine x. So this will be minus sine beta cos alpha. And again, just the reasoning behind it is that, where am I? Is that cos of negative beta is equal to cos beta, and sine of negative beta is equal to negative sine beta. So using that info. And this one is then done. See if you can get the other ones. Again, the difference identities are also on your formula sheet, but see if you can derive them from what we have. Take a moment, try that out. I will now do so myself. Again, I will phrase this as addition. And phrasing it as addition, I can rewrite things. Normally this would be cos alpha cos beta. Now it's cos alpha cos negative beta. And we'd be subtracting sine alpha sine beta, but now it's sine of negative beta. For the next step, I know that cosine is an even function, that even after I reflect it over the y-axis, I still get the same thing back. So I can just write this as that. And then similarly, I can say that sine of negative beta is the negative sign of positive beta. And then just taking a moment to expand, simplify those brackets at the end. This turns into a plus, and then I've got sine alpha, sine beta. And that one is done. And the last one is this nasty mess right here. I'm not the biggest fan of double angle, difference angles, or some identities with tan, but yeah, they work out eventually. It'll be fine. So again, phrasing it as addition means that I can use this in the addition, or yeah, the sum formula for the sum identity for tan, which on top would be tan alpha plus tan beta, but now it's tan alpha plus tan of negative beta. And on the bottom, it would be 1 minus tan alpha tan beta, according to the formula sheet for that, or on the previous page. So here would be 1 minus tan alpha tan negative beta. Simplifying things, I know that tan is an odd function, so tan of x is equal to, tan of negative x is equal to negative tan of x, which means that this turns into negative tan of beta, and on the bottom, this turns into negative tan of beta as well. So simplifying things, that's what we get. Done. Again, it's not necessary to know how to derive these things, but I do think it's critical in terms of gaining understanding as to why certain things exist. So we know where these formulas come from, or where these identities come from. Similarly, it's not necessary to memorize the derivation of the or the double angle identities that we're going to show on the next page. You just need to know how to use and apply them, but at the same time, it's very useful to have more of an understanding rather than just base knowledge. So with these double angle identities, that's where we have two of the same angle, we're going to express them as sums. I'll express this one as the sine of alpha plus alpha. And now I can use the fact that sine of alpha plus beta has its own formula. Something like that. And I'll replace all the betas with alphas, because that's what I've done here. So my next line of this would be to use the sum identity for the sine function. And say I've got sine alpha cos alpha plus sine alpha cos alpha. Again, it's like taking this one and replacing all the betas with alphas. And that's how we get this line here. From there, we just notice, well, this is the same thing as this. So adding something to itself means that you have two of that thing. Well, boom, done. And you can phrase this in terms of betas if you want, or you can phrase it in terms of thetas if you want. Whatever angle you want to put in there. It's just that they are the same. Note that we haven't just said something like, like sine of 2 alpha is 2 sine alpha. That is not the case, and that's not how this applies. Again, because of the way these functions are, the way that functions are in general, we can't just say we're distributing or that we can pull this out as if it's all just a series of multiplications. This is the sine of 2 alpha. See if you can get the formulas for the cosine of 2 alpha and the tangent of 2 alpha as well. Hopefully you've paused and now you're starting again. That's what I'm going with. And then, since cos of alpha plus beta is cos alpha cos beta minus sine alpha sine beta, I'm just going to take this and replace all the betas with alphas like that. So I'm going to get cos alpha minus sine alpha sine alpha. But cos alpha times cos alpha is just cos squared alpha. Sine alpha times sine alpha is just sine squared alpha. And that one is done. Did I put my little done square there? Nice. And finally, tan of 2 alpha. We'll work with this similarly. We have tan of alpha plus alpha. Whoops. And we'll use the sum identity for tan. That says tan of alpha plus beta is a whole bunch of stuff. 1 minus their product, I think it was. Let's just double check. Don't want to make sure we're using wrong things. Minus. Excellent. Super. Swell. Splendid. And to turn this into the double, we're just going to replace all the betas with alphas. That's what we're going to do. So we will write this as tan alpha, not beta anymore, alpha again, over 1 minus tan alpha, tan alpha. Oops. This top should have had a plus in it. See, there's this plus here. I should be using that here as well. That would have been bad. On the top, 2 of the same thing being added together. So I've got 2 tan alpha. On the bottom, I have 1 minus tan alpha times tan alpha, which is tan squared, alpha. And that one is done. Again, not necessary to memorize all those, but can be helpful just to have the understanding as to where they come from. Of special note is just this one for cosine, that we've got cos of 2 alpha is cos squared alpha minus sine squared alpha, and we can actually manipulate this a couple ways, and it's just based on the fact that sine squared alpha, or sine squared theta plus cos squared theta equals 1. So when we're looking at this thing, we can say that, cos of 2 theta is equal to cos squared theta minus sine squared theta, as we have up above, right over here. Right, so using that information, we can make this claim. But we could also say that sine squared theta is 1 minus cos squared theta. And that's because of that identity we had, that cos squared theta plus sine squared theta equals 1. I mean, I guess it's stated right here too. And then just moving things to other sides is how we get that manipulation, as we did in the previous video. As a result of that, we can say we've got cos squared theta minus 1 plus cos squared theta. We've opened up those brackets, which means overall we've just got 2 cos squared theta minus 1. Whoa, that's pretty wicked. In the same sense, we can say that cosine of 2 theta, again starting with that identity that it's cos squared theta minus sine squared theta, we can say that it is also equivalent to this. Replacing this cos squared theta with a 1 minus sine squared theta instead. And that's by the same rationale, by the different manipulations of this formula. As such, we can simplify this. Let's just drop some brackets as that, and finish it off with this. So we've got two other ways of writing cosine of 2 theta. It's really special like that. We love it, we cherish it, we adore it. If you want to take a break in this video, I think now would be the most appropriate time to do so. It's up to you if you have the will and the spirit and the drive and the motivation to keep going. Certainly keep going. But this can be a long one just because of all the proofs we did. So now would be certainly a good time to take a break, maybe even ask questions if you have any questions as to whatever went on in this video thus far. So please feel free to take that break now and watch this one in 2 installments. At this point, of course, I will be going ahead with the next installment, or the whole rest of it. We're going to write each of these expressions as a single trig function. Now, it doesn't say we have to evaluate or anything. It's just that we have to write it as a single trig function. Okay. Well, what we're going to look for is really patterns. Here I've got cos times cos plus sine times sine of some angles. And what I'm thinking is that this looks kind of like, well, it looks kind of like something to do with cosine, because we've got the difference formula, which looks like this, and we've got the sum formula that looks like this, right? Each one of them has a like cos and a sine involved. Again, it wouldn't be sine because it's sine cos, which is, if we look at our example right now, not what we actually have. Where's that example? So it's cos, sine. But is this a sum identity that we're going to play with, or a difference identity? Well, it's cos plus sine. And if we check our formulas for what has that, this one has it, cos plus sine. So we're talking about cos of alpha minus beta here. So this looks like cos of alpha minus beta, which is equal to cos alpha cos beta plus sine alpha sine beta. And reference your formula sheet as much as you want for this. Like, spot which one this looks familiar to. Now it looks like this, but we are replacing some things. It would look like that, except we're dealing with 72 degrees instead of this alpha. So all these alphas would be 72 degrees. And it's got these 49 degrees instead of these betas. So if we make these replacements over here, this will look just like this. And that means we can say that this function looks just like this side, but with 72 degrees for alpha and 49 degrees for beta. So we are going to do just that. We're going to say that this thing is equal to the cosine of 72 degrees minus 49 degrees. How would I double check this? I would say, all right, I've got the difference between two angles within this function, and I would just direct forward apply this rule to get to here and make sure that that ends up looking the same as what I've got there. If it's not, then I must have done something wrong. The only thing to do here is just to simplify 72 minus 49, and that's less than 30, so 23 degrees. That is done. Whoa! Little bit of a doozy. There are two more examples here, and they're not necessarily easy things because, I mean, we can whittle it down to say we're just playing a game of spot the differences, but that can be a tough thing to do. We're also trying to spot the similarities. So for these other two examples, see if you can find what this looks like and what this looks like on that formula sheet, or if you've memorized those formulas already, then in your head brain, and use that to try and determine how we can express each of those as a single trig function. Of course, this one we're even going to evaluate, but we'll see what happens. So try them out, see what happens. Hopefully you have, and hopefully you can now just check how your work went. I'm going to say that this thing looks kind of like the double angle formula for sine. It looks like we're saying sine of 2 alpha is equal to 2 sine alpha cos alpha. It's just that the alphas are actually 5 pi over 12. So if I replace each of these with 5 pi over 12, then I have this expression on the left. So that is just what I will do. Therefore, I have this, sine of 2 alpha. But not 2 alpha, I'm replacing those with 5 pi over 12. How interesting. And then, oops, I said over 6 over 12. Now I can say how interesting. How interesting. And just to simplify within those brackets, that's what we get. This is something we could actually evaluate. We do have the capacity to evaluate sine of 5 pi over 6. We just weren't asked to here. We were asked to express it as a single trig function. And that is what has been done. We should not be going any further with that. In this last question, of course, we are tasked with evaluating this. And he's got like pi over 12s? I don't know how to evaluate pi over 12s. What kind of madman do you think I am? That's something I could never see us doing, ever. Whoops. Certainly not on that page. We might do it on that page. Again, I'm looking for similarities between what I see here and what I might see in the formula sheets for the sum, difference, or double angle identities. I've got sine cos plus sine cos. If that is what I have, then I will actually say that this must look like the sum identity for sine. Sine of alpha plus beta is equal to sine alpha cos beta plus sine beta cos alpha. So that's what I'll be using. And I will be replacing all my alphas with pi over 12s. Oops. And I'll replace all my betas with 7 pi over 12. Just like that. So what I've got on this side is actually same as what I see here, which means that what this thing is equal to will be this left side right here. Let's get rid of all the excess here. And I can write that this is using the sum angle formula, or sum identity. So that's the sine of pi over 12 plus 7 pi over 12. Boom diata. And then for evaluating, I can just sum up the brackets. So we've got pi over 12 plus 7 pi over 12. So that's like 8 pi over 12. And simplifying that, 8 pi over 12 is 2 pi over 3. And sine of 2 pi over 3 is some, I don't know what it is. Here's pi over 3. This is and 2 and root 3. So it's some kind of root 3 over 2. 2 pi over 3 is over here somewhere, so it's positive. All right. So this thing is done. Whoa! What a ride that was. What a, as they say, doozy. It's not what I would say. It's just what they say. Just telling you what they say. There is some practice. Please, pretty please, do this practice. It is crucial and very necessary that you do that practice. And of course, it's necessary that you ask me all the questions that you have. So any questions that pop up for you, please just let me know, and I will help you as much as I can and as often as I can. Just ask me all the questions you have. So that's it. That's all. Give these things a go. These things a go. And let me know how it goes. I will talk to you in class. Take care and be good to yourselves.